Imagine you are pushing a shopping cart at a grocery store and then you try to push a car, obviously on a road. Same effort, completely different result. It means you're applying the same force onto different objects with different masses. That's exactly what Newton's second law explains, one of the most fundamental ideas in physics. Hi everyone, I'm Kuldeep. In this lesson, we will understand Newton's second law of motion, not just the formula, but the actual physics behind it. By the end of this lecture, you will be able to understand what causes motion, clearly able to draw the free body diagram, solve numericals related to this concept. Let's get started. Newton's second law states the net force acting on an object is equal to the product of its masses into acceleration, where the net force is basically the mass into acceleration m into a. Let's break this down. F net means the total net force acting on an object, including direction, because force is a vector quantity. And vector quantity means it has magnitude as well as direction. Mass represent how much an object resists acceleration, and this property is known as inertia. Acceleration tells us how quickly velocity changes. It means more net force means more acceleration, and more mass means less acceleration. And it's very important to know that acceleration always occurs in the direction of net force. It means the net force, if it is in the right direction, then acceleration would be also in the direction of the net force A. F is here the applied force. We will see the net force here. That's why it's much easier to accelerate a bicycle than a truck using the same force. Let's also remember the units. The force, the SI unit is Newton, or equivalent unit, we could say 1 Newton, right, is kilogram, 1 kilogram meter per second square. Now let's see the free body diagrams. These are going to give the strong concept clarity. To apply this law properly, we use the free body diagrams. In a free body diagram, we isolate the object and show only the external forces acting on it. Let's say there is a surface and an object is placed on it. Suppose a 10 kg box, that's the surface. We will see there is a normal force and there is a downward force, which is weight, which is mg, and this is the right force, which is applied force. And as it is placed on a surface or in a table, we will see there is going to be an opposite force just because of the inertia, an object or the surface. This is the friction. And let's say this friction is 10 Newton force and the applied force is 50 Newton's force. We will see these two vertical forces are going to be cancelled. So here the net force will be only is 40 Newton. So with the help of this, can find the acceleration, which is basically 4 meter per square in the right direction. As we have already discussed about it, the net force direction is same as the acceleration vector direction. So both would be in the right direction. Now let's solve a quick example. Suppose a 5 kg block is on a frictionless table. It means there is no friction. Two forces acting on it. One is 30 Newton to the right and 10 Newton to the left. This is the right direction or this is the left direction. This time it's saying it's not a friction force, but both are the two applied forces. As the table is the frictionless, there is no friction. The same problem, same concept. We will again see the net force is here again the 30 minus 10 is 20 Newton, and you will see the acceleration is going to be same, which is 4 meter per square. Here always we should always mention both magnitude and direction. You will see the acceleration is always in the direction of the net applied force. Now it's your turn. Suppose there is a box of mass 8 kg experiences a net force of 24 newtons. What will be the acceleration here? Okay, I think you will get the answer 3 meter per second square. If you got that right, you are on the right track. Let's recap the whole concept. The Newton's second law, mathematically written as that force is mass into acceleration, and always draw a free body diagram. The net force always includes direction, right? Acceleration follows the net force direction, follows net force direction. If you understand this result or this law well, you could solve mostly mechanics problem here. Thanks for watching. I will see you in the next lesson where we are going to discuss the 2D forces on an object. There we will see how the vector analysis is going to help to find the net vector, net force. Thank you.